I just want to remind you that the whole discussion about single carrier FDMA is to solve the PPR problem of OFDM, and we said, okay, we can reduce the PPR from the around 11, 12 dB of OFDM to around 8 dB in single carrier FDMA using the Dirichlet, the periodic sync kernel or pulse shape. But you know, if I would quiz the average engineer, communication engineer, say, okay, you know what is the PPR of single carrier? I think most engineers would give me a result that is around 3 dB, 4 dB. They would not give me a result. Actually, I did that. I quizzed the engineers and they gave me results around 3, 4 dB. They would not give you a result around 8 dB, meaning that most of them. Meaning that, okay, we've made progress, but I want more, meaning I want lower PPR. And the question is whether I can use similar techniques to single carrier FDMA, which is based on OFDM, OFDMA, and further reduce my PPR if I'm not happy with 8. So I'm discussing now PAPR optimized single carrier, or in short, POSC. And in POSC, we say, who says that a periodic sync pulse shape is a rule of nature? Who says that we must use periodic sync? Actually, you can even start with questioning even a more fundamental thing to single carrier FDMA. Say, you know what? I want to transmit M QAMs in the duration 0 to T. But why do I have to occupy the same number of subcarriers? Maybe I can transmit 8 QAMs on 0T, but occupy 12 subcarriers. Maybe I can occupy 6. Who says that I must occupy the same number of subcarriers as the number of QAMs that I'm transmitting over the period 0T? So actually, POSC is actually challenging this, two things. The first is I want to occupy a different number of subcarriers. I want to occupy Q subcarriers. And the second is I'm not necessarily so excited with working with the Dirichlet kernel, with the periodic sync. I want to have more flexibility. I want like a flexible pulse shape. So of course, this would be fitad. Of course, if I go back to Q equals M and I put GK here equals 1, then of course I go back to the regular single carrier FDMA. But essentially, I want to work with a more flexible, meaning that I occupy a different number of subcarriers than the number of QAMs symbols I'm transmitting in 0T, and also I want to work with a different pulse shape. For example, I want to include also these gains G of K for each of the subcarriers that I'm occupying. So if I'm considering this generalization of single carrier FDMA, let's take a look at what the transmitter would look like. So essentially, the transmitted signal that I want would be a sum. K goes from 0 to Q minus 1. Again, I'm occupying now Q tones or Q subcarriers. I'm replacing AK with GK times AK. This would be the input to my inverse FFT. And I'm reminding myself that AK, this is the DFT output of my QAM. Yeah. So a very important point here, maybe a nice tricky point, is that we used to think about DFT as a unitary transformation. I take M inputs, I produce M outputs, but here the sum is from 0 to Q minus 1. And let's say Q larger larger than M, how am I going to produce additional samples out of this DFT? So the interesting point here is to remember that actually AK, the DFT is periodic. Yeah. There are 8 M, let's say 8 inputs, but I can generate as many outputs as I want. It simply would be periodic if I'm considering here. I'm plugging any number K, I can get an output. But simply the sequence would be periodic in M, which actually means that we have a super low-cost implementation. Actually, almost the same complexity as single-carrier FDMA. And this says, okay, take your QAMs, apply M-point DFT. The green parts are identical to single-carrier FDMA. Apply M-point DFT to your QAMs, generate M-point sequence AK, identical to single-carrier FDMA. Now you want to occupy more tones? Okay. Cyclically extend the DFT output. So for example, you have 0, 1, 2, 3, 4, again 0, and then 1, and so on. Cyclically extend the DFT output. Apply simple frequency domain weighting, almost no complexity here, and then continue with the regular OFDM, OFDMA transmitter. So in terms of complexity on the transmitter side, almost identical to regular single-carrier FDMA. The key point here is that like I'm breaking these rules that M must be equal, the number of QAMs in 0T must be equal to the number of subcarriers, and that I'm using a Dirichlet kernel or pulse shape of single-carrier FDMA. I'm breaking these rules, and let's see what breaking these rules can bring. So if I'm like allowing a more flexible pulse shape, and I'm actually adding another minor detail, which is phase rotation between the OFDM symbol, just to minimize the phase transition. This is also hard-coded, so implies no complexity. So again, this is OFDM, PAPR, yeah? So 1112 dB. This would be single-carrier FDMA. And this guy would be POSC. So 1112 dB for OFDM, 8 dB for single-carrier FDMA, and around 3 dB for POSC. Again, the same essential modulator that is based on OFDM with a minor tweaking of the transmitter. And the cost for this is that actually I'm occupying 30% additional bandwidth or access. So I can trade off additional bandwidth for much lower PAPR, and you can imagine, again, from our discussion about information theory and what is the cost of multiplying your rate and so on, you can imagine that this kind of scheme can play a very dominant role in the low SNR, in the low SNR regime, where 30% access can be less important than a huge decrease in the PAPR. Yeah, if I'm working at very high SNR, probably 30% additional bandwidth or access is worth more than a few dBs. But if I'm working at the low SNR for the cell edge users, for the cell edge, this looks like this could be a very strong, very strong weapon. Yeah. So the key takeaway from this introduction of PAPR optimized single carrier POSC is just to give you an understanding that single carrier FDMA, which actually transforms the OFDM multi-carrier signal into a single carrier sequence signal with psych prefix is not the end of the road. We can continue to optimize it further, and very similar waveforms have been considered for 5G new radio and so on.